So this is not Fugaku supercomputer. This is K computer, the old machine that was just being decommissioned. But we don't have picture of Fugaku yet because it's not yet built. So, but it will be a near-exascale machine deployed in a couple of years in our Kobe site, and it's first-tier supercomputer in Japan. So this is Hyogo Prefecture. This is Japan, and the red one is where Kobe is, and that's the site where machine will be. And this is the nice artificial island we have, and machine will be just over there. This is how the node looks like. It has two CPUs built by Fujitsu, based on ARM V8 instruction set. It's water cooled, and it will be around 150. Yeah, this, well, yeah. Yeah. So this is how chip looks like. It's built on 7nm FinFET technology, and I guess this is the main number. Like this is like approximate numbers for performance, and for deep learning we are interested mainly in FP32, and for some cases maybe in FP16 performance. It has like one of the very nice features of this chip. It's insane memory bandwidth. It's around 1 terabytes per second. And the whole machine will have very nice high bandwidth fabric. And the performance of this chip is, among other things, due to SV extensions, which are sort of new flavor of SIMD, which is well, length agnostic extension. Is supposed to be easier to program with. And well, the bottom line of all this is that the whole system should be like very good system for deep learning. Like it's not AI purpose machine. It will run all the traditional HPC applications, but we want to run deep learning, particularly deep learning training on the system. But we don't have many deep learning frameworks which are optimized for ARM or for CPUs in general. So how do we do this? So imagine now that we discovered habitable planet in Alpha Centauri, and we know that Earth is doomed and the large meteorite is about to hit us soon, and we just have to get from here to there as soon as possible, because we don't just want to spend all the time on the flight. How do we do this? So there are options. We can just take our normal rockets, just make them bigger, beefier, and start flying. But it's only that fast that you can go with jet engines, because you need more fuel, need more mass, you need more fuel to accelerate that mass. It just doesn't scale up. We can stay on Earth and keep developing some new technology, some warp drive, which will just get us from here to there very fast. But we are not sure if we will be able to develop this technology anytime soon, like if ever. Well, we have some realistic options in between. We can use nuclear propulsion, and there are some, like, basically the technology is there, it just has to be polished a little bit. We can do the light sail. There are some, at least the physics is there to do antimatter drive or like black hole driven. And for people who are interested, there is a very nice episode of PBS Space Time going in depth on all these options. But the idea is all these choices come with the trade-offs, whether we can, start right away, but it takes longer time to fly it, or we just spend more time developing technology and then we fly faster. And the situation here is very similar. So, well, essentially, what we need to do is we need to port deep learning frameworks like there are some other aspects, but if you don't have deep learning frameworks, you just cannot do deep learning, basically. And deep learning frameworks are, well, it's a piece of software that enables you to do deep learning models, basically some extensions of a linear algebra, automatic differentiation, some helpers for training. And these frameworks doing kind of similar things, but there are many frameworks and they implement it in very different ways. And it's, as it happens, there are many frameworks which kind of within one framework have very different implementations internally. And partially it's done to support, let's say, different modes of training, or just because there was one implementation and they started doing new implementation, and then both implementations live simultaneously. So by different modes of operation, well, the most common case is so-called static and dynamic network graphs. So they are also sometimes called defined and run and defined by run. So the idea of models or frameworks which work using static graph is just to define your whole model, and then the model gets compiled, and then you run it. And in dynamic case, you just basically can execute each kernel independently, and it remembers your computation, and then it can do automatic differentiation just through the history of your computation. And the first approach allows you for some better optimizations, because you can know the whole picture, you can like rearrange some operations, you can fuse some kernels, etc. The second approach allows you to have more dynamics, let's say just if statements, loops, etc. And overall, the software stack of deep learning looks a little bit like this rough picture, and some frameworks maybe shortcuts through some of the steps and omit. But we have, should be, let me, oops, I pressed B button and everything disappeared. If I press it again, it appears again, nice. And the laser was the backside of the pointer. So you have your hardware, and you typically use some like basic compute libraries, like basically in the algebra subroutines, FFT, etc. It is not uncommon to have primitives specialized for deep learning. Recently, many frameworks introduce this intermediate layer, which is intermediate representation, and intermediate representation with some compiler. And on top of it, we have your basically frameworks, which is just your kind of user interface. And speaking about those two modes of operations, there are lots of ways, because people normally need both, and frameworks trying to simulate one with another is a by JIT compilation, and when you do JIT compilation, it's like several ways to do it. You can, if you have dynamic framework, you can first compute your model on some dummy data, and then take your computation history and JIT compile from it, but then you are at risk of missing some of those branches. Or you can look at the whole like Python code and just compile from it, as some frameworks are doing now. So this is frameworks we are currently sort of eyeing. PyTorch and TensorFlow are popular frameworks. Chainer has a special love in Japan, and also in some AI communities, like in NLP community actually. And we are collecting more feedback from our partner in AI centers to know better which frameworks do they want. And as I said, typically there are primitives which are used in deep learning frameworks like convolutions, LSTM cells, for which optimized implementations are typically hardware dependent. And you probably know, QDNN. Right, it's probably very widely used framework, very widely used library of deep learning primitives, and it's maintained by NVIDIA and used by many frameworks, right? And has all these kernels like convolutions, pooling, activations, etc. And it's even more than that. For each of the kernels, it's not uncommon to have multiple implementations, because which one is more efficient depends on your shape of your data, size of your data, the available memory. Some implementations take more memory, and you might not just have that much memory on your GPU device. But what do we have on CPU side? On CPU side, we have DNNL, which is formerly known as MKLDNN. We have also, since we are in the ARM world, we looked something called ARMNN, ARMCL. So the later one is basically just for inference, although we were thinking it might be a good place to implement the training support. It has many extra things which are useful for, say, more like old-fashioned vision tasks, like face detectors based on Hawk or something like that. It has some, basically for inference, it has support for deploying primitives, but those are mostly for Neon and for OpenCL. And for SVE, it's just BLAS there. And what we need to do is to just do deep learning training on CPU cores. Just no Mali GPU on those chips. It's core themselves. Now the other option is deep neural networks library, which was originally maintained by Intel. And basically, it provides roughly the same set of primitives, like convolutional kernels with BLAS, with Winograd, RNL cells activations, etc. Mostly FP32 format. The low precision there is mostly for inference. There are basically, if you look at the libraries, there are lots of assembly snippets for different Intel architectures. And this is what, I don't know, if I can already talk about this, this looks like Fujitsu will be doing the version of this for A64FX chips. It looks like. I mean, that should have been put at the end. So there is another sort of layer which we called intermediate representations. And well, if the first one was just, it sounds at least like it's a single primitives, like just a convolution, just a RNN, just activation. The idea of this intermediate representations is that you take the whole network graph and it converts it into some IR which can be optimized as a whole. But the line between those is a little bit blurry, because if you look at DNNL, you can first feed the whole network to DNNL, and it will do some optimizations for you. It will fuse kernels, for example. It's very typical to have activations and convolutions in just one go. If you look at TVM, like we are hoping to be able to just use individual operators from it. If you look at Onyx, which was just exchange format at the beginning, and I was like, what's the really difference between exchange format and intermediate representation? Now they're just was announced last week, they're rolling out Onyx compiler, which kind of makes Onyx like intermediate representation in a sense. So anyway, this not that clean separation between those two. Back to intermediate representations, there are like so many of them, basically everybody doing their own. Google is known for an XLA. Now they introduced a multi-level intermediate representation. There is TVM supported by Linaro. There is like lots of other things, Intel and Graph. They all say they're platform agnostic. Everybody should use them. Some people say it's just not invented here problem. Some people get very offended and say, no, these people don't do, polyhedral, and we do. It's just no. So I put a question mark there. Not making any strong statements here. But as the end user, they seem to solve roughly the same task. You give them your models, they compile model, and then you run the binaries, and you're happy. And well, one option we are looking at is TVM, which is IR plus compiler. It was originally developed for inference, so the idea was to just run your model on edge device. How am I on time, by the way? Okay, still 43 minutes. But training was recently added, and like we just looking now to which extent is it added and to which extent is it, you know, promising to be continued to support. Got some well, pictures from TVM. Basically, it's just exactly as I said. It takes the network, it compiles, and it also provides some auto tuning, which is nice if it can be used, and it just generates binaries for different platforms. This is like alternative picture of pretty much the same. It can sort of use different backends for compilations through like LLVMs, through OpenCL, etc. And this is not our benchmark. This is their benchmarks. Say, hey, we integrated with PyTorch, trains faster. So yeah, but this is pretty much work in progress by them and by us. Now let's look at what happened on deep learning framework side. So this is example of Chainer. Chainer is, well, if you know PyTorch, Chainer is pretty much the same on sort of user interface levels. There's some divergence now how they implement it, but originally they were just, you know, forks. This is defined by run framework, means it uses dynamic computation graph, means that you just can say, hey, do convolution, it will do convolution, and you will have some results in your variable, and then you just at any time can say, hey, just compute gradients from here to like back in time when whatever you were doing with this variable. Just basically like this. It's like doing computation with NumPy, except you can backpropagate through the computation. And at that time of when we started working at Chainer, the stack, the Chainer basically stack of the framework looked like that. They were using where is NumPy? Here's NumPy. They were using NumPy to do computation on CPU side. They were using CuPy, which was sort of drop-in replacement for NumPy, but just to work on GPUs, and it's by itself kind of interesting and useful package, I think. And well, there was also some Intel extension, also designed to be compatible with NumPy, but working on top of MKLDNN. And where is this? So by design, it was so that these backends have compatible interface, so you just can sort of program in very agnostic fashion. So XP here can become either NumPy or CuPy, and it just works. But in practice, it's not the most performant way. So the actual implementation of the same kernel has lots of, you know, if CuPy is enabled, if IDEEP is enabled, if otherwise something else is enabled. So it was very messy and hard to oh, this one is louder, and hard to extend. Then probably they were realizing themselves that it's hard to maintain, especially the developer of this framework, a Japanese company called Preferred Networks, came up with their own chips for deep learning. So they started redesigning the framework. They said, okay, now we have the new backend called ChainerX. It added a little bit more mess in the legacy code, but to here, but basically say, okay, instead of just, you know, calling everything from Python, we move, which is slow and one of the reasons to do this refactor, and we move the autograd part all in C++ backend, and well, this was a little bit developed. At this time, basically, PyTorch was facing the same problems that, you know, calling kernels from Python causes a little bit of overhead. They say, let's just JIT-compile everything. PFN people said, let's just move all this autograd fully in C++ and just keep Python as like wrappers for that. And because it was kind of new development, and they already realized, you know, from the mistakes, they, okay, let's make it very modular. Let's define some abstraction for the backend for the device, so it should be like easier to extend. Okay, now what can we do about like how do we bring Chainer to the ARM chips? Like because these codes, old code and new code, they live in parallel. There are multiple options. We can, we don't want to like port legacy Chainer. We can still use NumPy because NumPy is running on these chips. We can use their CPU backend, which is not optimized for ARM. We can create new CPU backend, which is optimized for this A64FX chips. Well, this we don't want to do because it is legacy code and will be gone sooner or later. We don't want to run on NumPy because it's inherently not as performant. So we either hope that the native backend will be fast enough, or we can push our changes, let's say using DNNL, to the native backend, or we will have to create our own like A64FX device backend and then put, let's say, all the bindings to DNNL library in this backend. Well, and the problem is that basically the CPU backend isn't optimized even for like more commonly used CPUs, and it's like low priority for the developers. For most of the frameworks, it's the case. Okay, so far we're using ndarray chips. Hope to run on real A64FX silicon stack soon. We're using Spark so far for managing the software on these nodes. We are looking at all these options like porting DNNL, using TVM, adding new backend to ChainerX. We are working, of course, with other frameworks. We are just independently of this, we are looking at performance of individual primitives. Few like more abstract points, since we are, I guess, rounding up soon. I guess for me as like a bit of AI person, it's also interesting to look at the models which are, well, we hope that the performance of the chips will be comparable with, say, modern GPUs on common deep learning problems. But deep learning is just not one thing. There's so many different models. Some models are, if anybody follows, let's say, what happened in AI world in language models, there recently this model called Transformers or BERT, which Google developed, and they sort of reaching state of the art in natural language problems. And if you look at the models, you just see clearly that these models were designed to run efficiently on TPUs. So because Google designed TPUs and they needed a model. So there are different models, run more or less efficient on different types of hardware. And I'm personally interested to look at the models which can run more efficiently on these chips, say, compared to GPUs. And this I see as a models with basically more divergence in them because they use hard attention, because they have some simulation parts in them. Okay, on the scale of the whole machine, what deep learning problems are, good fit? First of all, it's, of course, because of the scale of the machine, it's a large scale training. And also because of their very fast interconnect, it's model parallel. So model parallel is when you, normally when you do distributed deep learning, the common way is to do data parallel, when you just split your training set across nodes. Model parallel is your model is too big and you have to split the neural network itself. When just one side note, when you're training with at a large scale, just there's a problem not with compute but with machine learning parts, that if your batch size is very large, you not necessarily get the same accuracy. We're also working with research groups like to solve this problem using different optimizers. Also, naturally, our interest would be models which scale better with respect to batch size, like faster CNN object detectors, etc. Outside of the scope of this presentation, some other things that we are looking is basically optimizing scheduling of this, because you have many nodes, many people are using them at the same time. You have many options to parallelize. You can do hyperparameter search, you can do neural architecture search. We also have to solve somewhat I/O issues which we have on HPC systems with respect to deep learning data sets. And Okay. Some of the resources are on the GitHub deployment for Fugaku. There is not much there yet. Most of development is closed because of different restrictions. And last note, we have openings for postdocs in the research team. If you're interested, go to that URL. And thank you very much. And we have time for questions, I guess.
So one thing I did notice that was not included on your not included slide was any mention of inference on this machine. Are you targeting any inference type use cases, or is it purely on training?
Well, we are not targeting inference per se, though if you, like, so first of all, to do training, like when you do training, you have first do forward pass, which is inference, then you have to do backward pass, when it's like backpropagation. So if your forward pass is not fast, then basically it's bottlenecking your whole thing. So it naturally has to be improved. I guess one difference when people talk about optimizing for inference, usually they also consider small batch size, because if you do, let's say, face detection, whatever on the video, you want to process them frame by frame. So we don't have that restriction. I guess that's the difference. But inference with a large batch size as a part of the training, of course, yes.
Okay, so the supercomputers has been traditionally used for physical simulations, as Earth simulation, ocean simulation, whatever. Do you envision that this supercomputer, based on training, you can use it for training some models for this kind of simulations that traditionally use models, physicals?
Well, first of all, the machine itself will be, it's a general purpose machine, and it's mainly running like all sorts of like scientific workloads, including simulations. As for the intersection of AI and simulations, yeah, it's outside of scope of this work, but as a research team, we are of course looking at the problems when AI can augment simulation or vice versa.
Yeah, so people typically confuse this, right? So there's AI, when I kind of skipped over my talks, that's AI for HPC, and there's HPC for AI, which are two different things. So AI for HPC is to, just like you said, some sort of AI techniques enhancing computational capabilities, be it replacing traditional first principle kernels that drive data, like PDEs, with empirical-based empirical-based kernels, which you train, just like kids learning to look at water and being able to tell it's water splashing without being able to solve the Navier-Stokes equation. So deep learning equivalent of that is the AI for HPC, or try AI system enhancing like the management of the machines and so forth. There are a whole bunch of issues there. And then the HPC for AI is for HPC to accelerate deep learning training. Like I mentioned in my talk, compared to the first genesis of deep learning, rebirth of deep learning after 25 years of AI winter, was AlexNet. But the computational requirement of, let's say, something like AlphaGo is many orders of magnitude beyond what AlexNet had. So now it's a default that people use supercomputers for training, right? If you're not using supercomputer training, you're not doing competitive work in deep learning training. So so then you need machines, big GPU machines, TPU clusters, or machines like this. So so it's very important that we enable HPC for AI on these classes of machines. But the processors and networks have to be more capable, and as Alex mentioned, each has its strengths and weaknesses. know, TPUs are good for certain training, GPUs are good for certain training, and this machine will be good for other, you know, different classes of training. Although, you know, they can all, it's, you know, some are good for certain things. It's not they cannot do it, but, you know, there are certain areas where a machine like this will excel over, let's say, very large scale GPU clusters that, for example, the clouds currently have.
Let me ask you a question about the efficiency of the cluster interconnect. Like you use the TOFU, right? TOFU, that is you call 60 interconnect, okay, for the adjacent nodes. That is, it's be very efficient interconnect for your HPC application, like the vector forecaster, because the adjacent node interconnect with each other. But for the deep learning training, it basically is end-to-end connection because you have to change it, right? You have to do the SGD. So my question is, for your current system and the previous generation system, how efficient it is, okay, for your TOFU interconnect for the deep learning training application, and what kind of change you have to make to the SGD algorithm?
I'm not 100% sure how to interpret efficient, because what you mean, like joules per byte or dollars per byte. So this network is very capable. So it might be, let's say, overkill for some deep, for your typical data parallel deep learning training, where you just you don't need much latency. I mean, you don't need small latency. You just average over the large, just average your model weights across workers and just send them back. Well, there are multiple ways you can do distributed training. So I mentioned model parallel training, when your latency and basically overall your net connectivity becomes much more important, because you have to, if you do data parallel, you have to communicate once you process a mini batch. When you do the model parallel, you basically communicate within each sample. So
the question is, how efficient is the Fugaku's network over large, let's take large data parallel training. Okay, large data parallel training, basically the bottleneck is doing reduction. Okay, reduction sum, because you need to take the average, and TOFU is ultra efficient. It's much more efficient than any InfiniBand network, because there are papers about this, but basically we get theoretical maximum of the, and this was also proven to K, which also had the 60 torus. We get theoretical maximum on the injection bandwidth. All the way, and okay, we got this up to 88,000 nodes. So your statement, just to make sure that to comfort you, TOFU for deep learning is, we can get theoretical maximum injection bandwidth, which is like 30, on the Fugaku is at 38 gigabytes per second. Yeah, because there are ways to create these multidimensional reduction trees, and you get theoretical maximum out of that. And it's already proven. It's already done. So, yeah, ignore the latency. The throughput. You get theoretical maximum.
okay, then thank you everybody.